Hi everyone and welcome back to Nano World with Sandy. In today's episode 15, we are exploring how nanotechnology cleans water, covering nanofiltration membranes, nano-adsorbents and photocatalysts. If you like nanoscience made simple, hit the subscribe and follow me on Instagram at Nano World with Sandy. The world is thirsty. Water scarcity is a critical issue. A crisis rising due to population growth, industrialization, and especially climate change, bringing more droughts, floods, and contamination events. Traditional purification methods like chlorination, sand filtration, or reverse osmosis are becoming overwhelmed. They are often energy intensive and often inefficient for new emerging threats. We're talking about tiny contaminants like microplastics, pharmaceuticals, and heavy metals that traditional systems struggle to catch. This is why we turn to nanotechnology. By engineering materials at the nanometer scale, we drastically improve the three pillars of water treatment: separation, absorption, and degradation of pollutants. Let's dive into the first one: nanofiltration. Nanofiltration is the Goldilocks of membrane technology. With a pore size of about 1 to 10 nanometers, it operates at modern pressure about 5 to 20 bar, making it far more energy efficient than reverse osmosis. How they work? NF membranes don't just act like a simple sieve. They rely on two mechanisms. The first is size exclusion, blocking contaminants larger than the pore. The second is the crucial Donnan or electrostatic effect. The charged membrane surface actively repels similarly charged ions like Ca2+ and Mg2+, making it highly selective. Nanotech enhancement. This is where nanoscience elevates the technology. By embedding nanomaterials, we solve the two biggest issues: permeability and fouling. Materials like graphene oxide and carbon nanotubes are added to the polymer layer. They create highly hydrophilic channels and shorter diffusion paths, which dramatically increase water flow or flux without sacrificing purity. Even better, embedding TiO2 or Ag nanoparticles can give the membrane antibacterial or photocatalytic property for self-cleaning. The advantages: you get lower energy cost than RO, high removal for heavy metals and organics, and truly tunable properties. The challenges remain dealing with membrane fouling and ensuring the nanomaterials don't leach out into the clean water. Our second solution is nano-adsorbents. These materials are defined by their very high surface area to volume ratio. This tiny size means they have massive surface area, sometimes up to 1,000 square meter per gram, perfectly suiting for trapping pollutants. They trap contaminants through physical absorption, chemical binding, or ion exchange. This is a surface level attachment like a sticky trap. Common types: think metal oxide nanoparticles for capturing heavy metals, and carbon nanomaterials like activated carbon for binding organic dyes and pharmaceuticals. Nanoabsorbent must be synthesized, often via method like sol and gel or green biosynthesis. Then the surface must be modified to be selective. Once deployed, their major selling point is recovery and regeneration, especially if they are magnetic nanoabsorbents like Fe3O4, which could be pulled out and reused hundreds of times. Advantages: we get extremely fast absorption kinetics and highly selective binding. And the challenges: they can agglomerate or clump together, losing their effectiveness. We also need high efficiency regeneration processes to make them sustainable. Our final innovation is the photocatalyst, essentially a solar powered chemical cleaner. These nanostructures material use light to degrade pollutants completely into harmless substances like CO2 and H2O. How they work? It all begins with photon absorption. A photocatalyst, typically semiconductor like titanium dioxide, absorbs light energy. This light excites an electron from the valence band to the conduction band, leaving behind a positive hole. These charges migrate to the surface to drive powerful redox reaction. The hole reacts with water to form highly aggressive hydroxyl radicals, while the electron reacts with oxygen to form superoxide radicals. These radicals are extremely strong oxidizing agents that effectively break down organic pollutants, dyes, pathogens, until all that's left is a carbon dioxide and water. This is complete mineralization. The pollutants is destroyed, now just concentrated. Common nanomaterials. While TiO2 is stable and cheap, its primary drawback is that it only uses UV light, just 5% of solar energy. To fix this, researchers are doping TiO2 with elements like nitrogen or developing new metal-free catalysts like graphitic carbon nitride to increase efficiency under visible light. The key advantage is complete degradation and low energy costs since it's solar driven. Challenges are that resilience on UV light is still a major hurdle, and like absorbance, recovering the tiny catalyst particles once the reaction is done can be difficult. Nanotechnology is transforming water treatment from an energy intensive process into a smarter, more targeted, and sustainable one. By mastering separation, absorption, and degradation at nanoscale, we are tackling contaminants that are previously untouchable. But the real future lies in integration, combining these technologies such as self-cleaning NF membrane coated with TiO2 photocatalyst. In our next episode, we will dive into how these systems are integrated to help with climate adaptation, along with a deeper look at the limitations and future directions of this incredible technology. So thanks for watching, stay tuned and don't forget to like and subscribe.